Welcome to Train Signal. You're watching a video about network performance optimization. In this video, we're going to start off by taking a look at why we would want to have an optimized network. What are some of the reasons that we want to optimize our network? Because if we don't understand why we're doing something, well, then there's not a whole lot of point in doing it, is there? So after we take a look at some of these reasons, we'll talk about some of the methods, including QoS, which stands for quality of service, traffic shaping, load balancing, fault tolerance, and then finally something called caching engines. But first, why do we want to have our network optimized? What are the reasons? Well, one of the main reasons that we want to make sure we have good optimization is something called uptime. Now, many people actually refer to downtime on a regular basis. They say, well, we want to make sure we don't have very much downtime. Well, uptime is the opposite of downtime. Uptime is the measure of time that the network is running or that it's up. So different business solutions require different levels of uptime. Now, another term that is used that kind of goes along with this, and you'll hear this term kind of throughout this video, is something called high availability. High availability refers to, or it can refer to, a certain level of uptime. You may have a service agreement with a company to provide certain services to them with a guaranteed level of uptime. Because anytime that your network is not up, well, it's down. And when it's down, well, it's not making the company money anymore, is it? So uptime is very important. Now, another reason that we have for optimizing our network is something called latency sensitivity. Some applications require very quick delivery, which you'll notice I have here, and it's kind of spread out between two lines here, but low latency. Okay, that's what we mean by quick delivery. Low latency. Latency is the amount of delay in time for data to be delivered. So we want very quick delivery of this data in order to be effective. So an example of this might be some kind of voice over IP or video conferencing type application where you could imagine if you were having a conversation with somebody over a network, if you were saying something and then they didn't hear you till, let's say 10 seconds later, well, that would be very difficult to have that conversation then, wouldn't it? Matter of fact, we used to have to deal with that back in the older days when data delivery was very slow. If you've ever communicated via long distance telephone service, and I'm not talking about necessarily by today's standards, but going back a few decades, it used to be a little bit awkward if you were talking to somebody in another country because the amount of latency or the time it took for your voice to get from your telephone to the other person's telephone, well, there was a delay in there. And so sometimes you wouldn't know if the other person was done talking or just taking a breath, etc., etc. So this is another reason to make sure that we have a good optimized network. Now, the last reason I have here is something called high bandwidth applications. And quite frankly, this is not that much different than what we were just talking about in the sense that the type of applications that have high bandwidth would be things like voice over IP or video conferencing type applications. Those would be a couple of really good examples. And these are applications that require the availability of a very high level of bandwidth or a large quantity of bandwidth in order to transfer large quantities of data. If you're going to be sending video across the network, well, video is quite large in size. So we need to make sure there's enough bandwidth to allow that much data to be transferred. And quite frankly, you kind of put it all together, it has to be a large quantity of data transferred with low latency, just to go back to the latency sensitivity. So this is some of the why behind optimizing a network. Now let's take a look at some of the methods. Well, first here I have QoS, which stands for quality of service. Now, one thing you need to keep in mind is that quality of service is more of a strategy than it is an actual specific service. Now, there are different vendors who provide something they call quality of service, and it's an actual service. But overall, really, it's a strategy that's used to control the flow of network traffic, or to keep control over the flow of network traffic. With QoS, administrators can provide preferential delivery for the applications which need it the most. Okay, so it's a concept of being able to kind of control how much bandwidth is being used in different areas of the network by different applications and or different users. Now this leads us right into the next item here, which is called traffic shaping. Because traffic shaping is the actual method of shaping the traffic. That's kind of like, great, Ed, thanks a lot. Traffic shaping, shaping traffic. Well, traffic shaping is used to actually enforce the control of network traffic, whereas QoS is kind of a bigger picture of having an idea and a strategy towards where you're going to control data and how you're going to control data and when you're going to control data. Well, traffic shaping is the actual doing of it. Now, generally, traffic should be shaped based upon different priority factors. So we have these different factors, and some examples I have here would be either based upon users. So maybe we have certain users, and based upon their function within an organization, they need more bandwidth available to them for what they're doing than other users. And or we could be looking at applications for our priorities. In other words, certain applications we just talked about moments ago, voice over IP applications, video conferencing applications. We know that those need more bandwidth, so maybe we make more bandwidth available. But at the same time, maybe those applications are not as high a priority as other applications which might be transferring other forms of data. Now, another priority factor, which it's kind of a weird one, you don't really think about it, is time of day. You might implement certain priorities on certain links based upon what time of day it is and how many people might be present using the link at that point in time, etc., etc. So traffic shaping is where we're going to actually shape the data or have true control or enforce the control of data to different areas of our network, to different users on a network, different applications, different times, etc., etc. Now, load balancing, and sometimes you'll hear the term network load balancing, and we are talking about network performance optimization, so really we are talking about network load balancing here, but load balancing in general is a term which defines the use of more than one, and check this out, insert variable. Here's our variables down here. So we could say more than one server to provide a service, or more than one hard drive to provide a service, or more than one transmission line to provide the service. And there are other variables besides that. Those are just some examples. So we use more than one to provide a single networking service. Clients who are looking for that service, well, their needs are satisfied by either the first available, and again we have insert variable, or sometimes the needs can be satisfied by all insert variable. Okay, so let me get all this red ink off the screen here, and here's the bottom line. Load balancing is the concept of having more than one available, whatever it is, more than one of something available to meet your needs. And then you balance out that load between the different things that are available. Okay, and one of the most common that we see is probably servers. Okay, if you are providing DNS services on your network, odds are you aren't going to have just one DNS server. You're going to have two or more so that you can kind of divvy up that load between the different DNS servers. Now, when it comes to something like hard drives, this is a little bit confusing because in just a moment here we'll talk about something called RAID, but you can have an array of hard drives. So this is more on an individual machine. You have different hard drives that can provide the data. This is real common when you have databases involved and you're extracting large quantities of data. Or we could be talking about transmission lines. If we need to send data, maybe we're using more than one. Maybe we're doing what's called multiplexing, where we're sending data over more than one transmission line. That's what load balancing is. Now, something that kind of goes along with load balancing, in a way anyway, it kind of does, is something called fault tolerance. And the reason I say it kind of goes along with load balancing is because very often the purpose of having more than one of something is not just to spread out the load, not just balance it, but to also provide redundancy or fault tolerance. Now, fault tolerance, you'll see here it says if something is fault tolerant, then it means that in the event of a failure or fault, it will continue to function. And that would be what we mean by tolerance. Okay, so fault tolerance means that we have more than one of something running, but we're doing so for the purposes of, in the event that one of those things fails, well, then we have others to step in and take over. Now, fault tolerance, even though we're talking about network performance optimization, something you really need to keep in mind, in order to keep your network truly optimized, you need to implement fault tolerance at all levels of a network. And what I mean by that is we have our hard drives, okay, because if a server, let's say you have a server who's providing a network service, if there's just a single hard drive and that hard drive fails, well, then the server isn't working anymore. And by that server not working anymore, your network is not functioning properly. Power supply. Now, it's not so much the literal power supply in a computer box, although it could. It could mean having more than one power supply in a box. But I'm referring more to the concept of maybe using like an uninterruptible power supply or a UPS or battery backup. Because again, if power were to fail to a certain area, those computers would go down. So having backup there would be nice. Here's one that a lot of people don't think of. Network adapters. Believe it or not, it is possible to have more than one network adapter in a computer. Now that statement right there, most people are aware of. You can have more than one network adapter. Great. But I'm talking about where you have more than one network adapter and they are working in a fault-tolerant manner to where you have a form of failover, as it's sometimes referred to. If I want to borrow a term from something called clustering, which we'll talk about in a moment, but you have a failover to where basically you use the one network adapter, and if that adapter was to actually fail, well, then you could go ahead and use the other adapter. And I'm not talking about a user just going ahead and using the, oh, okay, I'm going to go use my other adapter. No, I'm talking about the computer automatically kicking that other adapter into action to take over for the first one that failed. Servers, I just mentioned the term clustering a moment ago when I mentioned the term failover. Well, clustering or server clustering is the concept of having more than one computer, so more than one physical computer, acting together as a single logical computer or logical server. And again, if one of the servers, and in some cases you can have real elaborate systems where multiple servers could even go down, you would still be able to provide the network services that those servers were designed to provide. Here's another one you don't really think of, routers. Yeah, very often it's a good idea to have different routers. And actually along those same lines, I'll just say we got the bottom one here, network links. You want to have more than one path to get from point A to point B. And by having these redundant paths, not only can you provide load balancing, which we talked about just a moment ago, but you also can have fault tolerance so that if one link or even if one router were to fail, well, you'd be able to find another route to get to your destination. Now, I will tell you, most of these fault tolerant mechanisms are fairly straightforward, and the details behind how you would implement them, like the literal details on how they would be implemented, would be based upon the actual vendor that you get your fault tolerance system from. But the one that is kind of a standard, no matter who you go with, is when we talk about fault tolerance of hard drives, well, we're talking about RAID. Okay, and RAID, R-A-I-D, stands for Redundant Array of Inexpensive or Independent Disks. There are different definitions. The I can be either inexpensive or independent. There is no specific 100% right or wrong. It's just the two different ways that it's said. Now, the first one that I have listed here, and there's three main levels of RAID that I'm going to go over with you right now. Now, there are more than three, but three I'm going to go over with you right now. The first one I have listed here is RAID 0, which stands for disk striping. That's what it's called, disk striping. Now, I'm going to tell you that this is not fault tolerant. Okay? So, just keep in mind that this first level RAID is not fault tolerant. It's just something you need to understand as a part of RAID. Disk striping is a concept where you will have two or more physical disks, and on the screen I have three drawn out here. And what happens is as data is written to these disks, and these disks, by the way, are going to work as a single logical area of storage. What's going to happen is that the data is going to be striped. So a block of data will be written here, and then it'll move over and write a block of data here, and then a block of data here, and then it'll come back over to here, and here, and here, and I have nowhere else to draw check marks, so come back to here, come back to here, come back to here, etc., etc. Okay, so disk striping is where we stripe the data across an array of disks. Now, you might be thinking to yourself, well, great, Ed, you told me it's not fault tolerant, so why would I ever want to use RAID 0? Well, RAID 0 is used strictly for performance reasons. When you are writing the data, you really gain no performance benefits. But when you are reading the data, you have the ability to theoretically read from all three of the drives at the same time. And remember, you have that data that's been spread out along all three drives. So you can read the different chunks from the different drives at the same time. So this will help you with performance and optimization. It just doesn't help you with fault tolerance. Now, the next level of RAID that I want to talk to you about is RAID 1. And RAID 1 stands for disk mirroring and duplexing. Now, disk mirroring and duplexing are basically the same thing, with just one specific difference, which I'll share with you after I explain what it is. Now, with RAID 1, you will always use exactly two physical hard disks. Now, again, these two disks are going to act as one logical area of storage. But what's happening here is that basically when you have some data, and that data is being written to a hard drive, well, an exact mirrored copy is being written to the other hard drive. So it's kind of just what it sounds like. Disk mirroring is just that. Everything you write to one disk, well, there's a mirrored copy on the other disk. And the idea behind it is if one of these disks were to fail, that's okay because we still have the data available to us on the other drive. Okay, so RAID 1, let me clear all this writing out of here. RAID 1 is fault tolerant. If one of these disks were to fail, we would still be able to continue writing and reading data on the other drive. Now, I will also tell you that RAID 1 provides a bit of load balancing. It doesn't really provide load balancing on the write side. Now, when I say write, I mean with a W, W-R-I-T, meaning when we're writing the data, because the data has to be written to both drives. Now, we have RAID 1 drivers out there which allow the data to be written to both drives simultaneously, so we don't really see performance loss. But where we have the load balancing is on the read end. When we're reading the data, because it exists in both places, we can read from both drives simultaneously, which is going to, again, improve our read performance. Now, before we go on to the next level of RAID, I said that I would explain what duplexing was. Well, duplexing is the same thing as mirroring, except for each of the two drives will be on their own separate hard drive controller. Okay, in your computer, you have a hard drive controller. This is what makes the hard drives go. Well, mirroring would be where we just have two drives on the same controller. And that is fault tolerant if one drive fails. But the problem there is, what happens if the controller fails? Well, both drives are down. With duplexing, we're taking this mirroring to a new level. We're still having the two hard drives, and if one drive fails, the other one kicks in, no problem. But now each drive is on its own controller, so that in the event that the controller fails, well, that's okay. It only takes one drive down with it, and we still have the other. Now, the last level of RAID that I specifically want to go over with you, and I mentioned specifically because I'm going to talk about a couple of other areas of RAID that I'm not going to go into great detail here. The last one is called RAID 5. RAID 5 stands for disk striping with parity. Now what this means is that the data will be striped across the array of hard drives just like we had with RAID 0. But here's the one difference. On each pass through the array, one of the drives, instead of writing data, we write what's called a parity block. And then this way, what happens is, if we have one of these drives fail, okay, so we'll say that this drive right here failed, what we can do is we can, through an algorithm, we can restore the missing data from this parity block. And that way, we have a fault-tolerant system. Now, the additional thing that I want to tell you about RAID 5, and I want to tell you about this with relation to RAID 1, is that with RAID 5, we have better disk space utilization than we have with RAID 1. See, with RAID 1, if we have two hard drives and each one, let's say, was 80 gigabytes, well, we would have a total of 160 gigabytes of storage, right? We have the two drives, so we'd have a total of 160 gigabytes of storage, but because they're being written as one identical copy of the data, we actually only end up with 80 gigs of storage, or like a single hard drive. Whereas with RAID 5, if these 4 disks that we had right here, if these were each 80 gig hard drives, we'd have a total of 320 gig of storage. But one of the drives is reserved for parity. But we still have data going on to the other 3 drives. So that means you end up with 240 gig of data out of the 320 we purchased. So here's how the math works out. With RAID 1, you always end up with 50% disk space utilization, meaning whatever you've purchased, you end up being able to use half of that, or store an amount equal to half of that. With RAID 5, you can use as little as 3 hard drives, which would mean that you would have 66 or 67% disk space utilization. But as you use more and more drives, so in this instance we used 4 drives, we have 75% disk space utilization, right? Because we had 240 gig of data on 320 gig of space. What if we had 10 drives? Only one's used for parity, 9 of them are used for data. That means we have 90% disk space utilization. So RAID 5 is very popular because you end up getting better use of your money that you spent on your hard drives. Now, the other advantage to RAID 5 is that your read access, again, is going to be improved because you can read from multiple drives at once, just like we could with disk striping, with RAID 0. Now, you might be thinking to yourself, well, what the heck? Why would I ever use RAID 1? I mean, RAID 5 seems to be the best of both worlds, right? You get the performance benefits, you get the fault tolerance benefits, you get to use a lot of your disk space. Well, there is one drawback to RAID 5, and that is that your writing performance is going to be slower. And the reason why is because we have to calculate the parity block every time we pass through and write data. So that's one thing you want to keep in mind when deciding which level of RAID you want to implement. Now, I mentioned that these are the three that I wanted to go over with you specifically. I will tell you that there are also other levels of RAID. There's RAID 2, 3, 4, which we're not even going to go into at all. There's RAID level 6, which is kind of like RAID 5. It is a form of striping with parity, but it's set up to where you can have 2 disks fail instead of 1 disk fail. But I'll tell you, some of the most popular forms of RAID these days are RAID 10, or technically it should be RAID 10, and then there's also RAID 01, and sometimes there's a plus in there, the way that's how it's listed. And what these stand for, whether it's RAID 10 or 01, it's like taking RAID 0 and 1 and putting them together to form a single level of fault tolerance. Okay, so one of them would be an example of having 2 stripes that are mirrored. Okay, so it would be like taking a stripe and then making an exact duplicate copy of that stripe and having it act as a mirror. Or we can look at it the other way around, which is where we can have 3 mirrors. Let me clear this out of here, because it's all just kind of getting confusing. But you can have 3 mirrors that are striped. Okay, so basically you can have each one of these mirrors acting as one piece of the stripe, so you end up with 3 mirrors. Now, another form of RAID that is out there today would be very similar to what we just talked about, but it would be either 1.5 or 5.1. And basically, I think you get the idea. It's just like what we had with 10 and 01, but now we're taking RAID 1 and 5 and bringing them together to form a really sophisticated level, or even multiple levels of fault tolerance. Because you can imagine if you were to take, and let me clear this out, what if we were to take each one of these mirrors and have it be one piece of this RAID 5 array? Well, what that means is you could have more than 1 disk fail. Because if 1 disk fails in one of the mirrors, well, that's okay, because the other disk is still running, and you have the other mirrors still fully functional. What if a drive failed in one of the other mirrors? No problem. Matter of fact, you could have 1 drive fail out of the 2 in each of the 4 mirrors, and you'll still have your RAID 5 array. Matter of fact, to go a step further, you could even have both drives fail in one of your mirrors, and that's okay, because then the parity would kick in, just like with RAID 5. And then again, we could also go the other way around to where we could have a RAID 5 array and then have that RAID 5 array be one part of a mirror and then have an identical RAID 5 array, which is the other side of the mirror. Okay, so you can get quite sophisticated with this, but I'll tell you what. If you can just familiarize yourself with RAID 0, 1, and 5, then you'll be fine. The rest of it eventually all makes sense if you just start logically putting it together. All right, caching engines. A caching engine is something that is used to store information so that it doesn't have to be retrieved off the network multiple times. And we already talked about one of these earlier in this course. A proxy server is a perfect example of a caching engine. Remember that a proxy server is used so that when one client makes a request of a certain website out on the internet, the proxy server will go ahead and, well, it'll do network address translation, right? That's where we learned about it, and it'll send that request out onto the internet. But then when that request comes back, before it sends it off to the client who originally asked for it, it caches that request. And why does it cache that request? So that when a second client makes the identical request, it doesn't have to use up bandwidth going back out to the internet. It just looks in its local cache and says, "Oh, I have that already. Here you go." So caching engines can be very important to the optimization of your network, especially when you're trying to keep control over the amount of bandwidth that's being used. If you have restrictions on the amount of bandwidth that's being used, a caching engine can come in real handy so as to be able to still provide what looks like real high-speed connectivity to your users when you've actually provided a very limited amount of bandwidth to them. Okay, well, at this point, you should be able to describe why it's important to have an optimized network. Remember that we want to have plenty of uptime. We need to keep latency sensitivity in mind when it comes to certain applications. And we need to have high bandwidth available for certain applications as well. And to be quite honest, what's the real reason you have to have an optimized network? To keep your users happy, right? Because users are going to complain when things are slow. Keep things optimized, everything works. You should be able to explain how an administrator can use quality of service and traffic shaping to keep control over the flow of network traffic. You should be able to explain how load balancing and fault tolerance are used to keep network services highly available. And you should be able to describe what a caching engine is. All right, well, that's what I have for you when it comes to network performance optimization. I'll see you in the next video.